Welcome back for another video about iron optics. Today we will draw, simulate and build a steering focusing iron lens with a simple design that can fit in any vacuum tube. I will start by showing you the SolidWorks design composed of 5 electrodes and 2 grounded mounts. Then we will simulate it in Simion and steer the ions such as the green ones. Finally, I will show you the results in a mass time of flight spectrometer because I will use the lens to mass select the ions. Here we go, the design is simple. The lens is supported by 2 grounded mounts. The external diameter is 95 mm because I use side pressure screws to ensure centering and secure the assembly in a tube of 100 mm of diameter. With few simple extrusions you can create the electrodes. I have 5 of them. A central one will be used for focusing, and I invite you to see my video about ions and lens to understand the focusing effect. Then I have 4 lateral electrodes, and actually they are the same than the central one but cut in 2. The position is shifted to operate a steering in the X and Y directions, but by applying a simple voltage bias. To assemble everything I use 4 M3 rods, and all the electrodes are insulated using small ceramics, so that there is no contact between the rods and the electrodes. These are the dimensions of the central electrode. The lateral electrodes are just cut in half, letting a space of 2 to 3 mm between them. Keep in mind that a lens like this creates spherical aberrations. As a result, only a quarter of the internal diameter should be used. Keep that in mind when you set your dimensions. If you really want to reduce the spherical aberrations at a minimum, you can try this diagonal slit design as described in this paper. Okay, now the Simion simulation. You can import the STL file into Simion. Check my channel for a video on that topic. In my case, I place my lens at a large distance from a benching accelerating unit to have a time of flight before the lens. You can fast adjust the potentials or use adjustable variable like me. My beam is coming at 1 kilo electron volt from the left, and I focus it by applying 800 volts at the center electrode. If I reduce this value to 400 volts, I will focus less the ions. At 100 volts, there is almost no focusing at all. Now, if I apply 200 volts on a lateral half electrode, my beam is deflected on the side. If I applied 200 volts on any other side electrode, the direction will change and will be different. Like this, I can really control the X and Y direction of the beam. By the way, in this simulation, I have an electron gun that ionizes the beam at a specific position. Then I have the acceleration and the bunch. A nice feature of Simion is that you can keep the display of a trajectory. If I go to my workbench program, I have a code that changes the color and the charge state of my beam when it crosses the electron beam. I can change the color from blue to green, then save the changes, fly again the ions, with now a deflection applied. And here you go, you have the display of both trajectories. What is really interesting is that you can pulse the voltage of any electrode so that you can get rid of a part of the beam. Okay, now let's build it. Every part can be manufactured in aluminum that is quite light, and you can drill a hole to screw an electrical connection and assemble everything together. It looks like that, and it's quite compact, and you have ceramics between each electrode to be sure that they are insulated each other. Let's go to my spectrometer instrument. There is a big, large chamber with a detector on one side and my lens at the opposite entrance. I connected every 5 electrodes on different power supply, and I'm using Benke to switch the potential as needed. You can appreciate the large turbo pump below the chamber and my own built detector. My ions will come from another chamber where they are accelerated and ionized. My ions are clusters created in a supersonic expansion with a pulse valve. My detector is connected to an oscilloscope and I'm using a delay generator to pulse my deflection. My beam is all the time deflected into the walls by a potential of minus 200 volt. Then I pulse this value to 0 volt, letting the ions hit the detector. I can change the delay and the width of the pulse so that I can select in time and therefore in mass my ions. In the time of flight, the same energy is given to my ions of different masses, and heavier ions are slower, so arrive later at the detector. Okay, to conclude, this lens is able to steer and focus the beam, and in addition, if you pulse the voltage, you can select in mass the ions based on their time of flight. With my instrument now, I can select in mass. I try with argon ion clusters. In this plot, several pulses are selected with increasing delay. To select a narrow distribution around, for example, argon 1000, I pulse the electrode at around 700 microseconds with a pulse width of 20 microseconds. Of course, you can optimize the ion signal by playing with the 5 potential applied to the electrodes.